Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome in to all of our viewers from around the world. Thank you for joining us. Please let us know where you are watching from. Also, welcome to listeners on the podcast version of SETI Live, available on most podcast platforms. In a collaboration between the Asteroid Institute and Google Cloud, algorithms have identified 27,500 new asteroids using existing data sets. And that's pretty spectacular. So I wanted to talk to Ed Liu, who's the executive director of the Asteroid Institute, about these results and what they mean for us. So Ed, thank you so much for joining me today. Welcome to SETI Live.
Thanks a lot, Beth. It's great to be here.
So let's get the first question just sort of out of the way. I saw that it was mentioned that there were at least 100 new sort of near-Earth objects in this data. Are there any planet killers? Do we have anything that looks like we're in trouble right away?
Okay, no. So I should explain what we were doing a search for new asteroids, and we, as you said, we identified tens of thousands of new asteroids that we've discovered. Now, some of those asteroids, most of those asteroids are in the asteroid belt, so that's between Mars and Jupiter. Vast majority of those. There are, however, a whole bunch of interesting cases that are not. There are ones that are further out, they're so-called trans-Neptunian objects. There are ones trailing Jupiter or in front of Jupiter, called Jupiter Trojans. We also have ones that are called near-Earth asteroids, and those are the ones that orbit in the inner solar system, i.e., where the Earth is. And so we've a few hundred of those, and those are the only ones that can hit the Earth, because if you don't enter the inner solar system, you won't hit the Earth, because that's where the Earth is. And what we have checked, though, is we do find that there are a number of these whose orbital paths come close to Earth's orbital path. That doesn't mean that the Earth and the asteroid are there at the same time, but it does mean that there is a chance of a collision at some point in the future. So we need to do a little more work to figure out the sizes of these things and so on. But what we do know is that there are a number of these whose orbital paths, for those who are astronomers, it's called the minimum orbit intersection distance, which is how close the closest point on the orbits is, and that's the closest possible point you can get to the Earth. Some of those are quite close.
Good to know. So we need more information is sort of the first part.
We'll get that. Yeah, just give us a few weeks. We're still working on this. This is all brand new.
Okay, so the Asteroid Institute is a part of the B612 Foundation. What is the foundation? How did this come about? Tell us more about your organization.
The B612 Foundation is an organization dedicated to protecting the Earth from devastating asteroid impacts. And we're a privately run, privately financed organization, much like SETI has been. So as we were talking earlier, we're a bit kindred organizations, and so I really love the stuff that SETI is doing. So the folks who are probably online have an idea for why you have organizations that are doing things that governments are also doing, right? Their governments are involved in astronomical searches. They do these sorts of things, but there is a role for, I think, more nimble, more cutting edge type things that can be done quickly by small organizations. And so our organization, the B612 Foundation, was founded 2 decades ago with this goal. And the prime issue for protecting the Earth from being hit by asteroids is finding and tracking asteroids. Because if you don't know an asteroid is on its way, you, by definition, can't do anything about it. So primarily what we're involved in is this issue of finding and tracking asteroids. And that's 99% of the battle.
Right.
Because deflecting asteroids, if you know when it's coming, as long as you have decades of notice, which is what you will get if you do your job right, is relatively easy. It's not among the more difficult of the space missions out there. It's been demonstrated by NASA, government organization, but there's been a test deflection of an asteroid just about a year and a half ago, and there will be future tests and so on. But the real issue is finding and tracking asteroids, and that's what we're doing at B612 Foundation.
So what inspired this particular search? How did this come about?
Well, most of the observations of the sky, the vast majority of them, are not done with the goal of finding and tracking asteroids. So they're done for other purposes, astronomy purposes, studies of galaxies, large scale structure of the universe, that sort of thing. But there are dedicated observatories which do look for asteroids. Now, these dedicated observatories have to observe the sky in a special cadence. And the reason is because what they're doing is they're looking for moving points of light. Now, remember, every moving point of light looks like every moving point of light because they're less than 1 pixel in size. They're just literally points of light. So if you don't take observations very close to each other in time, then you can't recognize one dot of light from another dot of light taken maybe months later or weeks later, or from a different telescope in a different place. There's no way to tie those together. So what observatories who search for asteroids do is they will take repeated images of the sky, like every couple of hours or less, looking for points that move just a tiny amount. And they go, oh, well, that's a moving object. And they'll do that repeatedly. But again, most of the observatories on Earth are doing other forms of astronomy. So most of the data is not useful at all for finding and tracking asteroids, unless you can solve the problem of figuring out which point of light is the same point of light on multiple images taken over time by even different telescopes. And that's a very difficult problem because I'll give you an example. We have a database of old observations of the sky taken by a number of different telescopes, multiple billions of objects that are moving points of light. They're there sometime and they're not there at another time. Okay, so that object is moving. And if you ask, and it takes in general a minimum of 6 observations of an asteroid in order to piece together the orbit well enough to be able to measure the orbit, know where it's going. Okay. So if I have, say, 5 billion observations, that's roughly the number we have. How many combinations of 6 different asteroids are there out of 5 billion?
Okay, that hurt my head. Sure.
And the answer is it's about 5 billion to the 6th power. So that's like 10 to the 57. So, absolutely ridiculous number. So you might say, okay, well, that's not possible. How do you do that? And the answer, so that's why the observatories who are looking for asteroids say, well, we're going to circumvent all that, just take rapid observations of the sky. And we'll look for things that just move a little bit. But we've been able to crack this by smart use of compute technology. So a couple of things have happened recently. First off was a breakthrough made by a guy named Joachim Moyens and his advisor, Mario Jurich, who are now part of the Asteroid Institute and B612 Foundation. This was the observation that you can actually match these things across if you simply assume a trajectory, take an orbit. Let's assume that this orbit is correct for n asteroids somewhere in this data set. And if that's the case, then I know the distance to that asteroid, right? Because I'm assuming an orbit. I know where it is.
Okay.
Now, if I know that, I can take every image of the sky and warp it such that it would be an image of the sky as if viewed from the sun, not from the Earth. Because I know the distance to everything in that sky because I have assumed a trajectory.
Okay.
Okay. So now, if observed from the sun, this is what that image would look like. Now, when observed from the sun, the orbits of things is very regular. Now, what I do is take all of my images across, months, years, whatever, from all my observatories, shift them all to, if observed from the sun, what would they look like, and stack them on top of each other. Okay. Now, if the orbit that I assumed was actually spot on, if there really was an asteroid on that trajectory, all of its images would line up right on top of each other because I have assumed the correct thing, and it would be centered in all the images.
Right.
However, it won't be exact because I just assumed something, and what are the chances that my particular guess is absolutely correct? It turns out, though, if you're close but not exact, the images won't stack up exactly, but they'll be clustered in a little line. You can search for that automatically. And what Joachim showed is that you don't need an infinite number of guesses to cover all the possibilities, such that you can actually find things that are close to any one of the trajectories. You only need a few tens of thousands of guesses to really find most of the things out there. And that means we can take that 10 to the 57 possibilities and break it down into something tractable. In fact, tractable for actually not that much compute. Not that much being the definition of not that much at Google.
Right. So this is a partnership with Google Cloud, because one of the things that was necessary here, obviously, was massive amounts of computing power. So this is not a simple run this on your home computer kind of function.
Oh no, we use many millions of CPU hours donated by Google Cloud, because they said, well, that's a really interesting use case, helping protect the Earth. We'd like to be part of that. And I also used to work at Google, so I know a lot of people there. And they were generous enough to both provide the time as well as some consulting help for our software engineers as we got our systems up and running on Google Cloud. And when you take this first set of data, we just picked data that we could get because it was publicly available online from other observatories that were, again, doing all sorts of different things, not asteroid searches. Right. So we grabbed a few data sets and about 7 years of observations, and ran it through this, and out pops 27,000 asteroid orbits. And so that's how we made those discoveries. Now, so I'd like to show a quick video if I could. Can you share the video? This is just a video. So these are the orbits of all the asteroids that we did discover just a couple of months ago. So there's the Earth. Now we're just sort of scanning back from the Earth. All the green dots are the newly discovered asteroids that we just discovered. So we'll start the solar system in motion. You'll be able to see where all these asteroids are that we just recently found. Now, we've only gone through a tiny fraction of all the available data sets out there, so we expect many tens of thousands of more discoveries that we'll make here over the next year or so.
Okay, and so what are the two red and blue lines, bluish lines we're looking at towards the center?
Okay, so those are the orbits of the planets. So you can see the in order: Mercury, Venus, Earth. You see the big cloud. You see what looks to be like a belt. That's the asteroid belt. So that's between Mars and Jupiter. You'll see some interesting clumps in the data. There's like sections where there's a lot of asteroids. Those aren't real clumps in the actual number of asteroids. Those are clumps in where certain telescopes have to be pointing at for a long period of time.
Right. Okay, that makes sense.
So we tend to discover certain things that, certain areas get preferential discoveries because it just so happens, for whatever scientific reason, some observatory was pointed in that direction. We pick up some asteroids as bycatch, if you'd like.
So think of it sort of like the Kepler observations, where Kepler was, for the first part, was just looking at one spot in Cygnus. And so, a lot of our exoplanet discoveries from that time period are just from there because that's where we were looking. So it's a similar bias.
Exactly. You make discoveries where your telescope is pointed.
Right. Okay.
And these happen to be telescopes that were pointed over a multi-year period, but you can see there were times when they were doing particularly active campaigns in certain areas. So we got a lot of discoveries too in those areas.
Okay, so I'm gonna welcome in people really quickly because we haven't done that yet, and it's a global audience again. So we have, let's see, San Francisco, New Mexico, Michigan, New Zealand, Germany, New Jersey, Poland, Azerbaijan. So thank you everybody for welcoming, and thank you for
locations of people around the world. I'd love to see it.
Yeah, it is. I love our audience. I love how global they are. So thank you everybody for tuning in. Once again, I'm talking to Ed Liu from the B612 Foundation and Asteroid Institute about the discovery in existing data of 27,500 new asteroids. And by new, I mean newly discovered, not magically appearing. They were there all along. We just finally found them. So Ed, how confident are you all in these discoveries? What sort of confidence level are we talking about with all of these little individual green dots we were looking at?
We're very, very confident. We actually discovered many, many thousands more that are ones that we would say not 100% confident in. So we're holding off on those, submitting those as official discoveries until we get more corroborating information, which is searching through more data sets for additional observations. And so we're holding off on a fair number of those still. But these ones are the ones that are highly confident.
So basically, this is like the baseline right now. So what you're saying is like
the beginning of it, yes.
This is the beginning. There's a lot more to come.
Yeah. We and to give you an idea how many asteroids this is, I believe last year there were about 16,000 discoveries by all observatories combined on Earth, and we did 27,000 in February and March of this year.
Wow. I can't wrap my head around it. Okay. If you have questions for Ed, please put them in the comments. I'm keeping an eye out and looking for those. So if you have questions about this, it's pretty astounding.
It's an interesting thing because we are currently, at least within the asteroid, and so we are limited by compute cycles, not by photons at telescopes at the moment, which is interesting. I mean, it's like everything else. Computation is becoming a bigger and bigger part of the things that we're doing scientifically.
Yeah, I definitely, I have noticed that, data science is becoming vastly important when it comes to all of our astronomical observations. So that I'm excited that you have this partnership with Google Cloud. That's great because, of course, obviously that means you are getting the compute cycles that you need to do this.
We are.
So what's next for the Asteroid Initiative, for these data sets? For where are you going with this project now?
Well, the next thing is there are many more data sets we have not yet ingested and gone through. And remember, it's an additive thing. You add it to the ones you've already had. It's not like you search in those individually, because now it's the combination of all these data sets from now telescopes all around the world. So, we have 5 different observatories data in there right now. We are adding several more right now. The biggest one will be the soon to be open Vera Rubin Observatory, which is a telescope in the southern hemisphere, which will be the largest asteroid discovery machine ever built. It is the largest one ever built, and it will have first light later this year. So we will ingest that data too and add it to this other data. And we believe we can improve the performance of the Vera Rubin Observatory, because its observations will now be combined with all of the other worldwide observatories, plus all of the historical data from all those other observatories that we can load up.
That's going to be, I mean, Vera Rubin's going to be I really truly believe it's going to be a game changer of a telescope for
multiple
a lot of astronomy.
yeah, not just what we're doing, which is solar system, protecting the Earth, mapping the solar system, but also for cosmology and understanding the large scale structure of the universe, the expansion of the universe, those types of questions. It's going to be an amazing machine. Been looking forward to this for decades now. I first heard about it 30 years ago.
It's going to do for ground-based observations what JWST has done for space-based observations. So, just the ability to get more detailed, more complicated, closer in, it's going to be amazing. Probably the thing that I'm looking forward to most is first light from Vera Rubin.
Yeah, me too.
So, I've got a couple of questions kind of coming in, but I want to know, like, what's next for you? What are you working on? Are you keeping your hand in this? Are there other projects at the Asteroid Institute or at B612 that you're doing? What are you going to be working on?
Well, this is a big part of it. The software side of asteroid discovery, mapping, analysis is really a wide open field. Okay, and that's what the Asteroid Institute at the B612 Foundation is working on: open source software tools for the astronomy community. Because we do know that we are, over the next next years from now, especially when Vera Rubin opens up, we're going to be finding asteroids that have a chance of hitting the Earth. I can tell you that just from the numbers that we expect to discover. And it's going to be an interesting time because we're going to have to make some decisions at some point about deflecting asteroids here. So I think it's very, very important that these tools be open source, the data be open, and that everyone show their work.
Mm-hmm.
And so I think the Asteroid Institute and B612 Foundation are at the lead of this open source trend in solar system astronomy.
Okay, well, I am super excited. Let's see what we've got for some questions here. I'm going to start with a friend of mine who's somewhat jokingly asking this, but I think it's a valid question too. So, does this mean we haven't cleared our orbit and Earth is going to get demoted to a minor planet status because we do have these things that are approaching our orbit?
No. There's other parts to being a planet. The definition of a planet, and size is a big part of it. Earth's pretty big, so
yeah. I don't think we have anything to worry about there.
Also, I think all the astronomers on, in the that exist that we know of live here on this planet. So
yeah, exactly. And I think that's kind of a key and very important there. Yeah. All right. So this one, okay. So how Fatmat is asking, how do you deal with interference from the sun? So are you taking into account like how that? Well, I think the question kind of comes from the point of view of, like a lot of the times these sort of what we call, sunward asteroids are really difficult to detect. So does your method overcome any of this somehow?
no, there's no interference with the sun. When I say as if viewed from the sun, I'm just talking about the positions of these things. Remember, they are observed from the Earth. From the telescopes are located on Earth. And what we're doing is transforming the locations of these things to the theoretical location of each dot of light if that telescope was located on the sun. So it's just a transformation of the position, the angle you would point at. That's all.
So it's mostly just like a mathematical calculation.
It is 100% a mathematical calculation.
Okay,
it is not actually, we're not doing image processing with that.
And that's where the computing time is needed, right? Is just running these calculations and having it say, here's this, here's this.
Yeah, again, we have billions of points of light, so you are and tens of thousands of test orbits that we try out, and and then when you do find things that cluster, then you actually calculate them. They have to go back and verify them. Now, I often get asked, was this artificial intelligence, machine learning type thing? No, that isn't what we did. This is really cloud computing, but there is an artificial intelligence machine learning step towards the end. Because what you do once, now we go into the verification step. We find a whole bunch of observations, say 20, 30 observations, points of light that look like they line up as an orbit. We calculate an orbit. Now we go back, we pull all the actual images and find the actual images of these things, and we go, let's make sure. So let's go back and take a look at these things. And what you find is that there are occasions when objects that appear to be moving are actually spurious data. It's something's located a little bit off because there's an overlapping galaxy or a nebula or something in the background that makes the position be, that can obscure the position. Or at times where you get just bad data because there's something like a cosmic ray or something like that that happens at high altitude observatories. There are cosmic rays. They do hit your sensors and so on. So what we did is we've been training a machine learning model to be able to clean out afterwards, like, hey, this data, this one, don't trust this one because there's a background galaxy right on top of it. The location may be uncertain. Or this one, hey, you probably are looking at a variable star in the background or something like that. The things that humans can tell. So we went through tens of thousands of these images by hand, building a training data set so that we can build a machine learning model so we can scale this thing up so that we don't have to go through things by hand in the future.
It seems like so much work. But I'm
Not bad
impressed.
for 5 technical people, huh?
No, no, not at all. Wow. Okay. Uh, Trey is asking. So first off, what is your relationship with the Asteroid Initiative? This is the Asteroid Initiative. So
Or the Asteroid Institute.
Institute. Sorry.
Yeah, the B612 the Asteroid Institute is part of the B612 Foundation.
Okay. Okay. I obviously am typing words in random ways. Okay, so what is your perspective on why we should be understanding these asteroids beyond keeping them away from Earth's atmosphere?
Okay, well, I look at it as the bigger thing of what we're trying to do is helping really build a comprehensive map of the solar system. We and all the worldwide community that's involved in this, because each one of these things is its own little world orbiting the sun, right? And they come big to small, from very small to very large. And then there are also planets. You can think of them as, the planets as being like continents, and these things as being, small islands. But there are many more islands than there are continents. Same thing is true with our solar system. There are millions of asteroids, but not that many planets. So the fact of the matter is that most of our solar system is uncharted at the moment. Now, why is that important? Because the orbits of these asteroids tell us about the dynamical history and evolution of our solar system and of the Earth. So if you want to do the science to understand how the solar system evolved, that's written in the orbital trajectories of these things, the clusterings of these things, the types of orbits that are prevalent. They're not random. And you can learn about the fact, the motions of the planets whose orbits have shifted during the evolution of the solar system and so on. So that's one thing. Obviously, number two, if any of them is on a trajectory to hit the Earth, we want to know about it. So that's number two. You protect the planet. And lastly, as human beings move out into the solar system, you need a map, right? You need to know where things are. It's the locations of resources at some point. It's the locations of, it's all the worlds in our solar system, right? And so, I look at it as sort of three big things, all encompassed under mapping the solar system. The same way we as humans mapped the Earth 500 years ago. Why do we do that? Because we were interested in understanding the Earth. We were interested in trade routes. We were interested in navigation, and so on. All the same reasons.
Absolutely fair. Science for science sake is not a bad thing, and understanding everything around us is a part of that.
Mm-hmm.
And I want to I want to kind of like wrap things up. We're getting to the end of our half an hour. Asteroid Day is coming.
Mm-hmm.
It is on June 30th. B612 has always sort of been a big part of that. Are there any events planned? Are there any talks planned? What do you have to say about Asteroid Day for our audience?
Well, Asteroid Day is, first off, for those who don't know what it is, it's an international day of acknowledgement of the work being done by and education of all the things being done in regarding asteroids. It's celebrated on June 30th because that happened to be the day that the Tunguska impact occurred, June 30th, 1908, an asteroid impact on Earth in Siberia. Now, the thing about Asteroid Day is all the events are individually organized by people. It was patterned after Earth Day. So there is no like one event for Earth Day. And there are literally many, many hundreds or even thousands of events around the world every Asteroid Day, cities around the world. So there will be similar. There are celebrations that I know of happening in San Francisco and Luxembourg and Australia. I think there's a number in Brazil, I think South Africa. I mean, they're going to be all over the world.
I love Asteroid Day. I mean, Tunguska is kind of one of those like watershed moments, and I think learning about that for me was just a major sort of eye-opening, wow, things can happen that you just really don't expect, and how to keep those things from happening. So
our goal is to expect it.
Yes.
Now, down to the second so that we can prevent it.
I mean that's the whole point of the DART mission, right? That was to see like can we make something move can we push something out of the way of Earth?
Yeah,
And
yeah,
we
and very successful.
very successful. Yeah, we proved
Yeah,
that yes, no, we
yeah,
can alter the orbit of a
yeah.
rock. Yay.
By the way, it's I think a better way to think about it isn't it's pushing it out of the way of the Earth. It's that you altered its trajectory by about 1/millionth of 1%. But that's enough to make it miss the Earth.
Mhm. Exactly.
Yeah,
I mean,
it
because
is an
we're not talking.
absolute.
I mean, it's not like Armageddon, right? We're not talking about taking a nuke up there and blowing it into chunks and hoping that all of those chunks
No,
miss the Earth. We're talking about no, get it early on, shift it just enough
yeah,
that
which
that
is an
orbit.
absolutely tiny amount. Like I said,
Yeah,
1/millionth of 1% is all you're doing, but
yeah,
that's enough to make it miss the Earth. There's a backside to that, though. There's a dark side to that. If a change of 1/millionth of 1% in the trajectory is enough to make it miss the Earth, that means to know if something's going to hit the Earth, you need to measure its orbit to with an accuracy of 1/millionth of 1%. And that's what we
right.
do. That is the kind of accuracy level that we can get, which is, I think,
And
amazing in and of itself.
and do you have that for these new asteroids, or is that still part of the process?
Not yet. Most of these asteroids still have what are called short observing arcs, meaning they've only been observed for days or weeks, that sort of
Mhm.
thing, or months at most. And that means that the uncertainty is much higher than that.
Right.
So, but you have a list of things now to go begin to, hey, this asteroid needs to have its orbit refined. Go look here, get the measurement, add it to it, refine it. It gives us a list of things to do.
There's a lot. It's a long list of things to do. You've now added 27,500 new lists of things to do.
Sorry.
Keeping our asteroid scientists swarming in work for a while. Well, thank you, Ed. Thank you to B612 Foundation. Thank you to the Asteroid Institute. Thank you, of course, to Google Cloud for providing the compute time for this. That is obviously an amazing part of it. Thank you for being here today, Ed, and answering my questions and talking to us about this. It is such important research, as you said, from a planetary defense perspective, and just from how does our solar system work and what's it really look like, to the details. So you guys are doing amazing work. Thank you so much for doing that and for being here and joining us today.
Thank you very much, Beth.
Thank you, everybody, for watching. Thank you, Julia, once again, for the stars on Facebook. Much appreciated. As always, the SETI Institute, as Ed mentioned, we are, us and B612 are nonprofit organizations. If you want to support us, please head over to SETI.org and click that Give Now button. You can also do the same thing for B612. You can head over to their website and support them if you want to do that too. So thank you for supporting us. Thank you for helping us keep these outreach programs running. We greatly appreciate it. And I will be back next week when I talk to Lisa Kaltneger about her new book, Alien Earths. So join us next Thursday for the next SETI Live. And thank you again, Ed, for being here.
Thanks again.